Hi everyone, welcome back to your calculus videos. So we are now into second semester. If you remember, last semester we talked a lot about derivatives and all the different derivative rules and how to find that. So this semester we're going to start talking about one of the other really big calculus concepts, which is integrals. Alright, so last semester we spent the majority of it learning how to find slopes of functions at one point. And we called these slopes derivatives. So last semester we talked about tangent lines, secant lines, normal lines, position, velocity, acceleration. We used derivatives in order to do some graph sketching. We did optimization and related rates. And then we used derivatives to help us make guarantees about functions using EVT, IVT, and MVT. So hopefully you remember extreme value theorem, intermediate value theorem, and the mean value theorem. Alright, but now we're going to shift gears a little bit, and this semester we're going to be learning how to find areas that are trapped between the graphs of functions, this should say and, the x-axis. And we're going to use these areas in application questions later on. It's going to be a big idea on the AP exam. So let's first start by taking a look at this notation. Alright, so the first thing you should notice is that there's this big, almost S-like notation right here. Alright, this is called our integral. And when you see this, this is telling you that you need to find the area. Alright, we are going to be finding the area trapped between a function and the x-axis. So this function right here, f of x, we're going to be finding the area between that function and the x-axis. Between this function f of x and the x-axis. Okay. Let's take a look at these other parts here. So we've got this a and b. All right. These are actually called our limits of integration. And all that does is it tells us where to start and stop finding the area. So we're going to start finding the area at x equals a, and then we're going to stop finding the area at x equals b. Alright, the other thing that I would like to point out to you really quick is just another part of the notation. So it always starts with this weird S shape, this integral, and it always ends with dx. Alright, you want to almost think of these like parentheses. This tells us, hey, we're going to take the area from a to b of this function, and the dx has to be there to help close it out. So we're never going to actually write something like that without this dx there. So you want to make sure that that is included in your notation. Alright, let's take a look at this next part. So the graph of f of x equals the square root of 9 minus x squared is given. So this is going to be a super important thing for you guys to take note of. You need to know that this right here gives you a semicircle. It's going to be super important for not just this chapter, but just in the future in general. You're going to have to know that anytime you have the square root of like y squared minus x squared or whatever it happens to be, that it's technically r squared, sorry, not y. This is going to be the radius of our semicircle. Alright, so you just kind of have to know that. It's going to make your life a lot easier in the future. Alright, so show what it means to find the integral from -2 to 3 of the square root of 9 minus x squared dx. Well, we know because we've got this integral that we're going to be finding an area. Alright, and it tells us that we're going to start finding our area at -2, so that's right here. And we are going to stop finding the area at 3, which is right here. So what that tells us then is the area that we're finding is trapped between that semicircle and the x-axis. So that means we're going to start here and we're going to go all the way to x equals 3. So finding the integral from -2 to 3 of this function means that we're finding the area of this blue shaded region right here. Okay? One more thing to talk about before we actually look at some examples here. We just want to talk about when areas are above the x-axis, so we're looking at some positive y values here, then we consider those to be positive areas. So for example, this region right here is above the x-axis because it's positive, or I'm sorry, it's positive because it's above the x-axis. And same thing here, this area would be positive because it is above the x-axis. And then this portion here, when areas are below the x-axis, they are considered to be negative. So this region right here would have a negative area, and so would this region right here. All right, so that's going to be something that's really important as we start finding these areas. So let's take a look at the next page and actually look at some examples here. So in these examples, you are given the graph of f of x, and we are going to use that graph to evaluate the integrals. And we're going to be using formulas from geometry. So we're going to be using triangles, rectangles, and semicircles are really the biggest ones that we're going to be looking at here. So for number 1, we want to find the integral from -3 to 0 of f of x dx. So we need to find the area that's trapped from -3 to 0. So when we're looking at this one here, we can see that from -3 to -2, the function is above the x-axis. So that's going to be a positive area. And then we can see that from -2 to 0, the function is below the x-axis. So that's going to be a negative area. And that's going to be important when we actually find the total. So I'm going to use the different colors here to help us kind of differentiate. So this orange triangle has a height and width of 1, or a height and a base of 1. So that would be 1/2 base times height. And then because the blue one is negative, I'm actually just going to go ahead and subtract it. But that's also 1/2, the base is 2, and the height is 2. So if we're looking for the area here, that would be 1/2 minus 2, and so we get -3/2 for our area here. And having a negative area really just tells us that there's more below the x-axis than there is above. And if we look, that definitely makes sense. There's more area down here that's blue than there is that's above that's orange. Okay? Now let's take a look at number 2. So number 2, we're looking for the integral from 0 to 4, which means we want to start at 0 and go to 4. And that whole area then is below the x-axis, so it's this right here, and then it goes to 4 and goes right here, and it's right here. Now this looks a little bit harder at first because we don't really know how to find the area of that stuff that I just made blue, right? But what we can do is we can find the area of this rectangle that's down here. So I'm going to go ahead and kind of outline it a little bit in this other blue. But that right there is a rectangle. And if I find the area of that rectangle and subtract off this semicircle, then I would be left with the area that's shaded. So I'm going to do the area of the rectangle in that kind of light blue. And I'm going to do the area of the semicircle in the red here. And hopefully you guys can see that we would be left with that blue shaded area. Okay, we're going to subtract those. So the rectangle, let's see, it's 2 by 4. And then the semicircle has a radius of 2, so that's pi r squared, and it's a semicircle, so it's cut in half. So we would have 8 minus, let's see, that's 4 pi divided by 2, which is 2 pi. And then what we have to remember is because it's negative, I'm going to stick a negative sign in front of this and just go ahead and distribute it through. So this area would be negative 8 plus 2 pi. There we go. That's our area there. So we want to make sure that because the whole thing is negative, we can just make it negative at the end and distribute it through like that. All right. The last one down here says that we're finding the area from negative 3 to 4 of f of x dx. Well, we can kind of use the pieces that we've done already because we already found from negative 3 to negative 2 was that positive area from before. And then we found this part here. So that first portion that I just colored was the first question that we did. So that had an area of negative 3 over 2. And then we also already found the area here, and then all the way to 4. We found that in question 2. So that was this negative 8 plus 2 pi. So we can actually just add that to here. And then we can add these together. So I'm going to make 8, I'm going to make that 16 over 2. And so our area is negative 19 over 2 plus 2 pi. That would be the integral from negative 3 to 4 of f of x dx. All right. And the last thing we need to talk about on here then is this other type of problem, which instead of me giving you a graph, you are going to have to make a graph of your own in order to be able to find the area using geometry. So let's take a look at this first one. We want the integral from negative 2 to 2 of the square root of 4 minus x squared dx. Well, this is that semicircle again that I kind of warned you guys about. So we need to draw ourselves a semicircle with a radius of 2. It's not quite even, but close enough. If I want the integral from negative 2 to 2, then that means I want this whole thing here, which is this semicircle. So we know that a semicircle would be pi r squared over 2. So it would be 4 pi over 2, which is 2 pi. And it's a positive 2 pi because it is above the x-axis. All right. For question 2, we want the integral from negative 4 to negative 1 of 3 dx. So this is a little weird. We have to remind ourselves that this number 3 is really just like saying y equals 3, which is a constant function. So if we draw a sketch here, 1, 2, 3, and 4, and then we'll go 1, 2, 2, 3. So we have a constant function going across, and we want the area from negative 4 to negative 1, so that would be here to here, so it's this entire area in here, which is just a rectangle. So we're going 3 by 3. That means that this has an area of 9. Question 3, we have a piecewise function. So let's draw ourselves this piecewise. All right, so it's a constant function for x is x is less than or equal to 2. So at 2, it's equal to 2. I'm going here. And it's going to be a closed circle because it is equal to 2. And then let's see, it's x for when x is greater than 2. So we're actually just going to 2, we would technically have an open circle, and then we're going to use a slope of 1. And I'm going to go one more value out, I think. And this is going to extend out this way. Alright, so for this one, we're going to kind of do it in pieces here, because we're going from -1 to 4. So -1 is right here, and then 1, 2, 3, 4 gets us to here. So we want this whole area, but what I'm going to do is I'm actually going to stop it here, and I'm going to do this rectangle, but then I'm also going to do this figure here, which is actually a trapezoid. So I'm going to go over to the side really quick, and just as a side note for all of us, area of a trapezoid is h over 2 times b1 plus b2. So remember, b1 and b2 are the parallel sides. Those are your bases. And then h is the distance between your parallel sides. So let's find the area of that rectangle first. So 1, 2, 3 by 2. And then plus, let's see, the height, so the distance between my parallel sides, which is 2. And then base 1, so that's right here, that's 2. Plus base 2, and that's 4. So this one was the 4, 2, and then this is the height, that's your 2. Just in case anybody missed that, sorry. And then we can go ahead and find our area. So that would be 6 plus 6, so that gives us a total area of 12. Alright, and the last one here, this again is a really important graph for you to know. So anytime we see this absolute value of x over x, you need to know what that graph looks like. So we're going to have a constant function. When x is positive, it's just constant at positive 1. And when x is negative, it's constant at negative 1. Alright, so you just need to know what that looks like, because it's going to make your life a lot easier, I promise. So here's 1, and then 1 and 2. And we want the area from -1, so here, to positive 2, which goes to here. So be careful here, because we do have some negative area right here. So that would be a -1 times 1. That's this rectangle, or it's really a square right here. And then we have a rectangle here that's 1 by 2. So we would have -1 plus 2. This would give us an overall area of positive 1 for that graph. Alright, so really the big thing that you need to know here is you need to understand what this notation means. Finding the area is just taking the integral, and then knowing that if it's above the x-axis it's positive, and if it's below the x-axis that it's negative. Alright, we'll do tons of practice in class, and I will see you guys later. Bye!